Welcome to Intro to Functional Programming in Haskell. Today we're going to be talking about laziness, basic libraries, and the I/O type. Haskell is technically a non-strict language. Non-strict and lazy are very similar. Their only differences lie in specifics that are beyond the scope of this course. And generally, even within the community, Haskell is referred to as a lazy language. So what does it mean to be lazy? Laziness just means that expressions are not evaluated immediately upon creation. They actually wait until they are needed to be evaluated, and only evaluated insofar as they need to be. When we use pattern matching to define functions, the underscore represents anything. There are actually two other special characters we can use in our pattern matchings. The tilde makes the evaluation of a pattern lazy, meaning we can use it to run a certain response to an input. However, it forces this case of the function to be lazy, meaning the items that we've pattern matched on will not be internally evaluated. So the tilde actually makes the case it is used on irrefutable. It will always match no matter what and execute its case. Preceding a pattern with the exclamation point makes a pattern strict. Upon matching within a function case, the arguments preceded by the exclamation point will be fully examined and evaluated. Now moving on to some basic libraries in Haskell. The language does have some benchmarking and profiling libraries, but that's not the focus of this course. The map library is provided within the language's core libraries. Map defines a map type. Maps provide key-based data access. Maps are akin to dicts in Python. They allow you to pair up keys and values and access them by the keys. One should note, though, if you plan on keying by numbers, it's probably more optimal to use hashmap, nmap, or vector. The set library is actually a hack on the map library. The set type is essentially just the map type, but all the values are essentially unit. Set is essentially then just a collection of keys with no values. However, if you look closely at the implementation of map, you'll notice that keys are forced to be unique and are also put in order. So set allows you to keep track of a set of unique values that are automatically ordered. Sequence is a kind of list that can have values added to its front and back. It is faster to traverse than list. However, you should double check using list because many times list is competitive with this and sequence requires a little more overhead. So unless you need the extra traverse speed or access to both ends of the list, you should look into using list. Up till this point, the closest thing we've been using that is akin to an array has been the list type. Haskell actually does have an array type, but most of the time that you're looking to use the array type, you're actually looking to use the vector type. Vector is a type that's built on top of the array type. Vector is useful when doing a lot of index-based accessing and for creating subarrays or slice operations. The string type is included in Prelude, Prelude being the library that's available by default in Haskell. String is a very simple representation of string that is actually just a list of chars. And while this representation is fairly simplistic, it is actually very finicky and slow. It's an inefficient way to store textual data. It results in slow indexing that takes linear time, and there's also issues generated by the fact that lists can actually be infinite. The text library addresses many of these issues. It stores textual data in a UTF-16 encoding that is much more memory efficient. And finally, the ByteString library is another way of storing textual data. However, it actually just stores sequences of bytes as word 8 values in a vector. And while this is a convenient way to work with data, one needs to be aware that one can accidentally store non-textual bytes within the underlying vector, and be careful in analyzing those word 8 values, knowing that they may or may not contain true text values. I/O is a type. We've been using it up to this point, but haven't really clearly explained what it is. It does have a monad instance, but it's not just a monad. One way it is accurately described is that it's a state monad, where the state is the real world, meaning I/O actions take the real world, meaning the state of the bits on your computer and the state of other things in the world, do something, and that action of doing something produces a new state. That action has an effect on the real world, producing a new real world. But this really only encompasses what I/O allows for conceptually. As far as what I/O does within the language, it simply prevents the reordering of code by the compiler, as well as the sharing of information. Having an I/O of something is different than having some sort of type container of some other kind of value, like a just 5 or a maybe of an int. Having an I/O of A represents a way to get an A, not an A value wrapped by some I/O type. Whenever we evaluate an I/O A, we are executing a recipe to get an A value. That A value could be different if we evaluate the I/O A at a different time.